Hello, hello. Okay,
Good
hello.
morning.
Good morning. Thank you, Marissa. No, who? Sorry, who? Good morning.
That was me.
Oh, good morning. Okay, thank you, Just. Good morning, Justin, and good morning, Sarah. Got that? All right. Good morning,
Good
Sarah.
morning, Professor.
Good morning, Marissa. Thank you. Good morning, Jenna. Here we go. I love this is becoming my favorite part now. I used to hate this so much. Okay, wait. Good morning. Wait. Okay. Good morning, Jenna. Good morning, Andre. Good morning, Kimberly. I mean, hello, Kimberly. It was fine, thanks. Oh, sorry. I mean, good afternoon, Andre. I mean, good morning, Jenna. I mean, good morning, Sarah. I'm loving this. Good morning, Rachel. Good morning, no, good afternoon, Alyssa. Well, time's like flowing from student to student. It was like morning, now it's afternoon within the same chat. Good morning again, Armin. Back to good morning, Sheeran. Good morning, Abby. Good morning, Alea. Good morning, Ali Nelly. Good morning, Erica. Okay, cool. So I think it seems like the consensus is that we're still in the morning, not the afternoon. I'll buy whatever you guys. Time is relative. If you took the first course, or okay, wait. So good morning, everybody. Oh, sorry. Good morning, Yalbo. Good morning, Aaron. Good morning.
Good morning.
Good morning. Hi. Did I say oh wait, more people. I think that, and if I didn't say you, I'm sorry. I think, wait, someone just came in or no one just came in? Someone just came in? Okay, I think we're good to go. Okay. Yeah, okay. I think we're good to and I think we can hit the ground running. Oh, wait, sorry. Pardon me. Yeah. Okay. Right. Okay. We can hit the ground running in a second, I think. I think if I've done my homework correctly, if I've done my homework correctly, yeah, you are the class that is. So you are very on top of homework, you guys, very much, um, in all ways. I believe that as of last night, anyway, anything that any one of you have done of any kind, which is a lot, like all of you are, I mean, really, but if you did anything then as of last night, hopefully you've gotten it back. Like I think I was all caught up after, if you handed in anything this morning, then that's great and it's not late or anything, but then I haven't gotten to it yet. But if you handed in anything before this morning and you didn't get it back, please check, or like maybe something's wrong. And I mean anything. Now we're starting to rock and roll. Like we're like a lot of people got in homework 3, which is great. And I think a lot of people found that homework 3 was much less stressful than homework 2. Please still nonetheless do them in that order. We're going to get back to homework 2 right now. This is funny. But I know the one, so you guys really, I'm very pleased with this class. There's one thing that I owe you really, and I hate to bring this up, so I'm going to bring it up to not bring it up. There had been some discussion about a midterm at some point, and even maybe we had even nailed down a date. Now I seem to have flown in the face of that date. Like I think whatever date so what I'm getting at very quickly is on Wednesday, this Wednesday, I want to keep tracks right now. We're getting momentum. So I want to stay with the physics we're doing and that you guys have been working on at home. And I'll continue to take any assignment that you have not handed in yet. I will take happily, and I'll take any update, anything you've not gotten a 50, without a doubt. Even if I didn't say it, if you didn't get a 50 on something, there's always a way to rehand it in and get the 50, like for any of you who care. And it may not be worth it in some cases, but it might be, blah, blah, blah. But what I'm trying to get at is I kind of pleasantly forgot about the midterm, and we're going to forget about it today again. On Wednesday, we will rediscuss the midterm. That is, like, I will make a commitment to give you a review pack and all that kind of stuff, and you'll have time to, I mean, in other words, we'll reconfigure the date if we have to, if now we're past the point where, but we'll do that Wednesday. Wednesday, we will confront the midterm, but not today. So that said, but I'll take any other questions on any other, again, that's just because my bad, because I just don't feel like dealing with it. So we're dealing with it Wednesday, but anything else that comes up, please stop me. Anything about homework or any of this material. But if not, what I think is, I feel like I must be forgetting something that's too easy, but I feel like we're in the middle of math methods going over. We were just about to get to the juicy stuff with E. Or we just did start the E thing, I think we did, right? So you'll refresh me in a second, but I believe, maybe I will ask someone to remind me in a second. Hang on. like I think the last thing we wrote was the very first example that had an E in it, and we found that it wasn't a solution. But and I believe it was called Part 1I, but someone may want to confirm that for me in a second. Well, yes, okay, here. Yeah, I would hope so. So I'm gonna.
Yeah, it is I.
Thank you so much. I very much appreciate that. And so it's Part I, capital I of Part 1. Okay, thank you. And it was, and if this is right, I know we wrote it yesterday, but oh, it didn't have it. Was this what I should take out the sheet myself? But is this how it was phrased, or there was no X naught in it? It was. Okay, I'm just going to get the sheet. One second.
It's omega square negative omega square times x.
But was this the function that was? But the function that I agree with you that that's the derivative. But was this the? Hang on. Was this the actual? Oh! I said it. Oh, I see what you're saying. I'm sorry. I see what you're saying. I think. Oh yeah. I'm sorry. Okay. I see the sheet. What you're saying. Hold on. Okay. And someone's trying to get in. I am aware. Or I thought someone was trying to get in. It's not someone trying to get in the waiting room. Well, okay. My apologies. Right. Here's the question again. And I know we already did set this up, but I just want to catch us up. So the question was, is X equals E? Okay, thank you. All right, right. So this is literally saying in English, and Yabo is someone who was raising like good questions about this when it first came up and in the homework, but others did as well. Like what this is saying in English is if it's saying that this thing in black that I'm writing down now that you're getting increasingly familiar with, hopefully, like if you're starting to get bored of this thing, that's great, right? If you're starting to get bored of seeing something that looks like this, that means that you're getting comfortable with it, which is good, because that's what we're saying over and over. This thing in black is just the mathy way of writing harmonic oscillator, right? This thing in black means, in fact, not only this is a harmonic oscillator, and specifically it's like something going back and forth in space, whereas if X were Z, it could have been any kind of harmonic oscillator, but this thing means some kind of harmonic oscillator. And what we're now asking is, well, we've been describing our harmonic oscillators with cosine functions, which really makes sense, not only mathematically, but because like cosines go back and forth, and our oscillators in our minds go back and forth cyclically. But what we're raising the question now, like math is supposed to be the language of physics, like for good or for bad. We're not saying, but we're doing this math. We're seeing through the math, like universal relations behind the physics, underneath the physics. And now we're saying what we know from math is that cosine worked as a solution, not only because it had the right picture, but also because when we differentiate it twice, we get back to itself with a negative sign or with a times a constant. And that was a good thing. Well, then we remembered. And frankly, like some people in the class, like including Yaverbaum and other people remember, like, wait, E does that also. E is that kind of function. It's not a polynomial function. It's not an algebraic function. It's not a power function. It's a different kind of function where rates of change yield itself. That's very inviting. That's the kind of thing we're talking about. And let me also say, in fact, I will definitely say, Okay. Like this is mathy stuff, but this is really physical stuff. What we're really saying, if you're following me, like the reason we're spending so much time on differential equations and why we're making such a hoopla over them, like why there's such a specific thing, is because a differential equation has a circular reasoning to it. It has a self-referential quality, a very interesting quality that is either a very intimidating, impossible, challenging, like contradictory quality, or a very exciting quality, depending on how you think about it. But that quality is called feedback. Like every differential equation is saying that a rate of change of effect with respect to cause is a function of effect, right? The whole thing that makes this a differential equation is that what's on the right side is the dependent variable, not the independent variable. It's such a technicality, right? But it is such a big physical difference. It's saying, now let me remind everybody right now, I want to remind you why we're doing this math stuff. You're like, what does this have to do with physics? And you really will see. But for me, I understand each one better. And I think of it this way. Excuse me, someone's coming. Sorry, I'm getting all excited. But I am excited. I love exponential transcendental functions for this reason. Like the differential equation that we have, if it seems hard at all, or if it seems like we're making a big deal, there's a reason. Because from the get-go, when we said it's differential equation if it has an x on the right side, but like if it just had a t, then it was just like do an integral. Like that's what we were saying from the get-go, that it's not just an equation that has a derivative in it. It's equation that relates the derivative to the dependent variable, which in English is like saying that the rate at which some effect changes with respect to its cause depends on not the cause, but on the effect itself. Like what does it, like that is crazy. Like remember what this is like. Here's a common example that you often learn in math class, but it's like I go to the bank and I say, guys, I know I have an interest-bearing account at the, like this is all a lie because I'm a professor, so obviously I don't have it, but I go to the bank and I'm like, I have an interest-bearing account at this bank. Like that means you're supposed to like give me interest, like my money sits there, but it like grows interest, right? You give me money for letting you use my money, right? So I want to know how much is in my account right now. And they say to me, well, Professor Yaverbaum, that depends on how much interest we put in your account yesterday, right? Which is true, right? Like, because even if I put in 100 yesterday, that wouldn't be what I would have today. I'd have like 101.2 or something. So if I say, how much do I have? They're like, well, it depends on how much interest was put in. So then I'm like, okay, how much interest was put in? And they say that depends on how much was there, right? Like that's what interest means. That is, you should pause and realize that's a little bit crazy when you hear that. There is a reason we have to do weird math to unpack that, because that's a weird idea. The amount of money that I have in my account depends on how much interest was added, but the amount of interest added depends on how much is in the account. That is like a mirror looking at another mirror and trying to find an image. Like, right? I'm not saying it's impossible. Apparently it works. Apparently banks do this, but it does. But what we're talking about in any okay, sorry, I know there's something in the chat and I'm totally like losing my, but when all these words, differential equation, dependent variable, feedback, I'm saying you cannot, the reason a differential equation is at all interesting or requires math is because from the get-go, it's saying there's some kind of loopy thing going on somewhere where cause leads to effect, but effect causes effect. And it, like, however you want to say that. And so it makes sense that the solutions that we look for are functions that talk to themselves in the same way. We want a function where the rate of change of it somehow does depend on it. That's that same loopy, weird idea. It's kind of like two rights maybe make a wrong. Like two weird, we need self-referential math to describe this self-referential physical system. I'm going to pause for a second because I know things are happening in the chat and I'm probably losing here, or I'm losing my job, or I'm losing my something. Hold on a second. Chat. Oh, good. Oh, thank you. Oh, wait. Oh, wait, this is great. Okay. Wow, cool. I'm glad, totally. I'm glad these chats are about it. So wait, so Alea's first, the left side of the differential is the independent. The independent variable is the independent, that very fair question. Whenever you see any derivative at all, any like D thing over D thing, the independent variable is always what's in the bottom, the denominator. Like that's the one thing we know. Yes, what's in the denominator would be, what's in the denominator is always the independent variable. And what's in the numerator is always dependent. And that's a really good question. It's not a stupid question, y'all. It's a good question, partly because There's no other way to know. Like X could be sometimes independent T. Like I'm not saying the law comes from Moses or something, or whomever. I'm saying that we can only tell what's independent dependent by how that fraction's written. It is a rule you can rely on. If you see derivatives, whatever's on the bottom, because it's rise over run. A derivative means rise over run. Run is this axis, rise is that one, whatever you call them. It's like, and this is like a cause, and that's like effect. If you want to, so what's crazy about a differential equation? What's crazy about this all goes back to what's crazy about, and then I'm going to get the other, but I'm cool. But I mean, I'm psyched that Sarah's saying she never, hopefully this is helpful though. This is why these things mean something to me. And believe me, again, anything I'm saying now, I get excited because at some point I understood this. I did not understand these things the first 50 million times I did these things. Really, like, and a lot of times we feel like we can't do them unless we understand them. It doesn't work that way. You don't get to understand them until you just like kind of force yourself to do them, sort of like, you know, playing scales or whatever. But on Leia's question, what I'm ultimately then getting at, everything we're going to say from here on in about waves and electricity, magnetism, it all comes back to the weirdness of a mass on a spring, that a mass on a spring goes back and forth. And in any moment, we want to know, okay, where are you? Like, I just want to know, like, where is the mass at some moment in time? Like, that's all physicists ever want to know. You name the moment in time, and can I name the position in space that our desired object will occupy? Like, that's always, so we're looking at a mass going back and forth, and the physicist wants to say, okay, if you name the time, could I name the place? And what happens with a mass on going back and forth on a spring is, what we find is, Professor Hooke says, well, in order to do that, you just need the accelerate. Like, remember your good old physics, you'll need the acceleration at any position. If you can say the acceleration, then we can tell you what position it'll be at. And then we say, okay, well, how do we know the acceleration? I mean, it's not constant, right? So how do we know the acceleration? And they say, well, it depends on the position. That's literally what's going on here. All of this is blowing up because because the position of an oscillator, maybe you should even write this down. All of this is happening, all this crazy math, not because we're looking for trouble, but because the position on an oscillator, the position of an oscillator depends on its acceleration, but the acceleration depends on position. That's literally what we're saying. That's the knot that we're trying to untangle, that weirdly we can untangle with cosines and stuff, but we're saying once we untangle that knot, oh my God, there's a lot of knots in the universe just like that apparently we can untangle now. And whenever we do, we're looking at feedback. Whenever we untie a differential equation and get a solution to it, we are writing out a feedback phenomenon in a way. We're turning something that looks like circular reasoning into something predictable. And the functions that, and we'll try any function that seems like it would work. So now bringing this finally full back, sorry, and I'm getting all, but I mean, really, this stuff is like, it's the nectar of the tree as far as I'm concerned. But if I get back to this differential equation now, what some people in the class are rightfully saying, and what Hooke or Newton would say is, oh, if cosines are a good way to describe an oscillator, in a way, shouldn't exponents also be good? Because we remember from calculus, the derivative of an e function is an e function. So part of our brain says, let's try some e functions. But then another part of our brain, and again, this applies to some people in the class, are saying, but that would be weird if that does work, because e functions don't go up and down. They're like, they either feedback positively or they feedback negatively. Exponential functions are always like exponential growth or exponential decay, not a coincidence. They're monotonic. They blast off to somewhere, they blast out somewhere. So how the heck could that describe an oscillator? That's the question on the table. It's the scientific question is, wait, on the one hand, shouldn't an exponential function work here? And on the other hand, shouldn't it not? So we try. And I mean, that's the question of I. And I know I did it already on Friday, but I'm just going to quickly do it again now, just hopefully if any of this perspective does anything for anybody. And just always try to approach the stuff of, I wonder if I can get this. Don't approach the stuff like, I don't get that. Like, right, because you don't until you do. Like, no one does on the first time, even people that think they do. So I'm saying, what are you saying, Yaverbaum? Get a new job, Yaverbaum. No, I'm saying, well, if the function that I'm trying, so they're having me they're not even putting a x naught, they're just saying, try this exponential function. Like, we got to throw an omega in there somewhere because of units, yada, yada, so try that. if X, well, then I'm going to try. I'm going to do what we've been doing, like till hopefully we're almost bored because we're getting so good at it. We said, well, then the derivative of E by chain, and I know we did this, but by chain rule and by the habity hoobity, everything is that. And then we do it again because we're checking a second order differential equation. So then we go that, but then the negative sign, right? And everybody, so then we go, to bring us back full circle where we go, no. Well, maybe you see that, maybe you don't, but we go, no, it's not, because evidently d equals like this thing was what we were trying as X. So evidently what we just found was this, which looks pretty good, but we wanted like that. So I'm saying apparently this conjecture, this exponential function, it did satisfy a differential equation. Like, don't get me wrong, like what I just wrote here, what I'm writing here, that is most certainly a legitimate real differential equation. It's a second order differential equation. Totally, you can do math with it. It just, but it doesn't have a negative sign. So it doesn't mean it's wrong. It just means it's not our differential equation. That's not an oscillator. That's not Hooke's law. There's no restoring force there, right? Which is not, so it's almost not a surprise. Like, oh, E didn't work. E blasted us off in some direction and is not restoring us. Almost not surprisingly, it didn't work because what we wanted a negative sign there if this was going to work, right? So what we found is no, the exponential solution in a way doesn't work, right? And that's sort of satisfying because it kind of doesn't seem like the right shape. It kind of seems like it shouldn't work. But on the other hand, like it's only off by a negative sign. So what we might do, and I forget if the homework then does this. So now moving on. So that was, oh yeah, like before I move on to J, what one might do very quickly. So this is I continued. So I'm going to very quickly right now, like it doesn't say this in the homework, but if I'm actually trying to understand this or be thorough, like the reason I got no for my answer to part I was because I didn't get a certain negative sign that I wanted. But because I put a negative sign in, but it went away. So it's reasonable to try. Like, what if I don't put a negative sign? Maybe that was the problem. Maybe it went away. Let me just try the other case. And also maybe just if you're following, like, I've got to have an X naught in here somewhere. If it's going to be the right kind of physics, like, I don't need to assume that X naught is 1. It could be anything. And that should still probably work. So let me just try, right? I'm just trying. I'm still on I here. But if I try this, I'm just doing it quickly again to make a point. I mean, you guys can throw this in the chat if you want, but I'm saying if I try this now, do one derivative, well, the X naught will just stay there. The omega will, sorry, actually I should do it like this. The omega comes out, the X naught stays there. So I get this. And then I do it again. So the omega comes out again, the X naught still stays there. And I still get, like, just to check, like, oh, it still doesn't work. Like somehow I'm off by a negative sign, E doesn't do it. And in a way, that would be good. I mean, in a way, I feel like that's not shocking because E does seem like a different kind of function. But now I get big for my britches now. And I throw in this new math thing that one might have thought has nothing to do with physics. I all of a sudden, so now I'm moving on. Okay, now I'm just moving on. Sorry, it's 12:40. I will take a breath at some point in my life, but of course I always say that and blah, blah, blah. We're in J now. All of a sudden now, J introduces what is in a way a whole branch of mathematics, but in other ways just a fact, or it's just, just a definition. It's just saying from here on in, let's use this symbol I to stand for the square root of -1. Now, many of you have heard this before. Some of you might find this exciting. Some might find it intimidating, but I'm literally just saying that. I'm saying from here on in, whatever the square root of -1 is, let's call it I. I'm reminding you perhaps that the reason I would even go to that trouble, like I'm not renaming all the numbers in the world. Like I don't want to give a name to like the square root of positive one. But the reason I don't want is because I already have an answer to that. Like I like remember, and you may want to write this down, but like a positive times a positive equals a positive, and a negative times a negative equals a positive. So whenever I'm looking for a number which, when multiplied by itself, gets me a positive number, positive numbers and negative numbers will work. But no number that I know of multiplied by itself will give me a negative number, right? Because positives times positives give me positives, and negative times negatives also give me positives. The only thing that ever gives me negatives is a positive times a negative, and some positive times some negative is not something multiplied by itself, right? So we just take this concept of -1 and we give it a name called I. And then we just assume that any other rules that we already know about math still apply. Like this is just a symbol for, it's just kind of calling something X, we're calling it I, right? Now, there's a reason that I would even think to introduce this now. I'm going to show you that reason. Like this seems completely out of nowhere, especially in a physics class. Like it might even seem obnoxious in a math class. Like where did I all of a sudden come into the discussion? But particularly in a physics class, it might be very curious that I'm introducing something called an imaginary number. Now, look, as far as I'm concerned, in a way, all numbers are imaginary. I'm not, I don't know why it's imaginary. I do know that it's just different kind of number. But all I have to know is how square roots work and how the number line works. And I will see in a minute why I would even have introduced it. Like what I'm trying to get at is this does relate to physics as much as any number relates to physics, but you have to understand what kind of number it is. So I'm going to take the first given I, I'm going to throw an I. Key thing is, by the way, no matter how fancy it looks, whatever, it's still a constant. I should say. I'm sorry. Whatever I is, it's not going to change. It's a constant number. It's just a new kind of number. Okay, using that kind of number, I'm going to conjecture, because you knew I was onto something with this E business, and I like the omega t, but it wasn't quite working with the negative signs. So I'm thinking maybe I will help. And by the way, look, why would you could already maybe see why I might even raise the issue of I is I had like what our problem here is like positive times positive equals positive and negative times negative equals positive, right? Like that's exactly the problem that we're getting into here is that we're looking for a negative sign to appear, but we can't make it appear by an omega when we multiply, like whether we make omega positive or negative in effect. Either way, we multiply by itself. In fact, actually, this is totally my reason. I don't know why I didn't think of this before. That's our problem with the negative sign is no matter how we try to stick the negative sign into the exponential, it multiplies by itself because it's a second derivative and goes away. Or if we don't put it there, a positive multiplies by itself and the negative goes away. So we're trying to create a negative out of thin air. That's exactly where the whole idea of I came from in the first place, trying to create like the square root of a negative. So look, and that's my best reason. My reason doesn't have to be perfect because I'm just going to try now and see what happens. So I do. I try, remembering that I is a constant. Actually, maybe I should here. I'll pause here now. Maybe so. I'm going to pause. I'm going to ask anybody in the chat, privately, publicly, or say it. Please do this derivative, and you can do the next one too. Assuming that I is all you have to know about I is exactly what I just said. It's a constant number that is the square root of -1. Then can you please get the first derivative of x equals e? I mean, you did it for homework, but if everybody right now could even put it in the chat or whatever, and I'll wait till I get a bunch of answers. It's not a race. But the question is, or did I lose? Sorry. Yeah, the question is this and this. And so I'll wait till I get some in the chat or vocally, just so everybody can catch up and breathe. Again, this is part of the homework, but whether you did, thank you. I just saw one in direct chat. Thank you. Oh, I saw two in direct chat. Awesome, awesome. And both people in the direct chat are totally cool. Totally awesomely correct. In fact, those two people could go on to the second derivative, would be great. But yeah, and I'm not trying to, this is not right, but I just want to make sure everybody take a breath and catch up. We're doing what's on the sheet right now. Even if you already did for homework, you're either copying from your homework or you're thinking about it for the first time right now. Cool. I'm seeing things happen. And I'll start responding. So again, I'm just going to take a couple minutes so people can catch up. Oh, and some people putting in the great. Oh, I'm just trying to respond to people. Great. I see things are actually happening in the and I'm not going to say right or wrong about the main chat. So in the main chat, it's not a race. If you think you're right, like put it in. Even if someone already put it in, I'm not saying if it's right or wrong. So just put it in if you want. Or I'm responding to the direct chats as well. I like calling them direct, not private. I guess that's a better name. And I don't know. You know that person. Oh wow! Oh, and someone put a thing in the thing. Oh, that's great. All right. I say awesome, it doesn't necessarily mean right. It just means awesome. Like, thank you for putting in. Sweet. Right. Sweet. Okay. No, that was good. Oh, nice. Okay. Cool. All right. Now I'm going to say this is good. Now we have a lot of people responding. This is good. I really appreciate it. And I want to say again, I'm not trying to be cheesy, but every single one of you, and I haven't acknowledged yet, like Kimberly, Marissa, Alyssa, and again, I'm technically I'm not saying right or wrong. So there's no reason anybody couldn't still now put something in, like, right? But I am saying, and seeing if someone's even correcting themselves. Okay. I'm literally saying, I'm just trying to acknowledge every single one of you that put anything anywhere, whether you put in the private or you put in the public and different, please do submit these for points in the game terms. I'm like, really mean it. And if you want me to open separate portals for whether it's private or public, I can do that too, whatever. But like, you should all, like, it makes a difference that you're all doing this. Like, and I want you to know that I know that you're paying attention and all that. And there is even a screenshot here that I'm tempted. Can I? Well, it was put in the. I mean, not to, but since. Well, okay, fair enough. Okay. Yeah. Just to very quickly, like, I think I don't know why, but okay. All right, actually, yeah, no. So there's a screenshot. There is a. Well, let me put it this way. There's a PNG that did get shared with everybody in the chat. Maybe it was sort of unintentional, but I definitely approve of the PNG. I was about to explicitly share with everybody, but it's not even worth. But you all, the PNG that is in the chat, it definitely is right. I mean, I'll say that, and I think it looks good too. I won't. No. It's fine. But I just realized I'm gonna have a technical thing that gets weird with my board anyway. But to everybody, all right. I think a lot of you got it right. I mean, yes, we're doing chain rule. So good that we're all together. That's cool. And I think we get chain rule and all that. But also this now is going to show us something, I think. Like, I agree with you all that if you do chain rule the first time, then you bring down the I and the omega. Sorry. Just to you you bring down the I and the omega, and then you still get times e to the I omega t. That's the first derivative. But then the second derivative, by that same logic, the second derivative, you bring down the I again, so you get I squared. You bring down the omega again, you get omega squared. You get e to the I omega t. But now here's the revelation that a lot of you have, but it's worth noting, is that, oh, whoa, if all I have to know is that if I by definition is the square root of -1, then by definition I squared is -1, right? Like that's that's just by definition. So apparently we have so that's interesting because, oh, weird, that works, right? Like I does have exactly that property. So apparently, so I mean, so that's yes, right? So the answer is yes for this one. Apparently, if you put something as strange as exponentials together with something as seemingly not real as imaginary numbers, apparently that gives you the same effect as a cosine. Like that, like somehow we can describe oscillators with exponentials as long as we're willing to make them complex exponentials. It's very strange at first blush. It's almost like saying, it's like sounds like it's saying two wrongs make a right, or like as long as we can describe this oscillatory behavior with something completely non-oscillatory, as long as we add an ingredient of non-reality, that of imaginary numbers. That sounds bizarre. Why would that make sense at all? Well, remember, this has to do with feedback. This is all our physicists' attempt to capture feedback. Oscillation is one kind of feedback. Growth or decay is another kind of feedback. But the root, the kernel between the two is feedback. So two things I want to say, like, okay, so right, this is literally our question now. It's like, why is it that we can add complex number, not add, but like engage complex numbers with exponential functions in order to describe oscillatory behavior? Like what? And why do I care? Well, one reason is feedback. Is that what is in common about all three things is feedback. Hold on. Okay, so the answer is feedback. I'm going to quickly show you what I mean in one way in which I mean that. Remember, Okay. One thing, sorry, let me just, okay. I tried to say that I came in because we were trying to like, oh, cool. Thank you. That's a nice thing to say. Yeah, I kind of feel that way too, Andre. Yes, thank you. Right. Good. And clearly Andre gets the point. I mean, like, or what is the point? I mean, there's different points, I suppose, but a point I'm trying to make here is one reason I brought up I is because we have like this negative positive sign issue that we want to reconcile. And in fact, I was invented in the first place to reconcile an issue like that, or discovered in the first place. But the other thing is that I clocks in cycles of 4, just like sine and cosine do, right? And then that's what I think Andre is noticing here. That's what I'm trying to say here is that it's not even just so like E refer the derivative of E. And by the way, I could put, I guess I really should, like if let's take this, you know, if like what I'm trying to say is we have these 3 functions out there, or these 3 concepts or something: exponential functions, trigonometric functions, and complex functions. And what I'm saying is, in general, what they all have in common is some kind of feedback, some kind of looping, some kind of referring to themselves. Now, what I'm saying even more specifically in mathematical terms is actually that they all can be lined up in cycles of 4, including the exponential loops in cycles of 1. Like the derivative of the exponential is itself every time. So whether you wait 2 times or 3 times or 4 times, you're going to get back to the exponential. Well, if you wait 4 times, you'll get back to the sine, right? I mean, again, I'm just spelling this out, but you know, if you take trigonometric derivatives, you just have to wait 4 turns and you'll get back to where you started. And right, if you are raising I to powers, and by the way, remember, whenever you take a derivative, you're kind of raising to a power, right? Or you're lowering to, I mean, it's, so when you raise I to a power, if you do it 4 times, you get back to itself. This doesn't prove anything. I'm not proving anything here. I'm trying to show a relationship and show why, and this is, you know, why I would come into the discussion at all. Let me just chat. Hold on a second. Oh, cool. Oh, great. I'm very psyched. Okay. So yeah, so and this is where math gets more and more fun. I mean, really. I mean, and just again for the record, I love math. I'm not going to pretend I don't. I want everybody to love math, but I didn't always love math. I love math because it is lovable, and because in fact, the more I hated it when I hated it, the more I love it now, and it's possible for everybody. Also, I'm not trying to sell to anybody who doesn't need it sold. But don't give up on math, even if you had a terrible experience to now. I had terrible experiences with math for years and years and years, but that's not math's fault. Anyway, and also, you know, remember, you can be wrong at math, but math will never wrong you. Like math doesn't hurt people's feelings. Math doesn't break up with people. Math doesn't like storm and rage out your apart. You know what I'm saying? Like math is clean. It's just intimidatingly clean. But okay. But so all right. So this. So now I'm going to find, now we could do a whole course. So the truth is we're going to get it eventually into circuits and stuff like that. And circuits are always described. The easiest way to describe circuits, whether they're oscillatory circuits, RC circuits, and we're going to get into it. I mean, everything moves fast, but absolutely people use I to describe circuits. They describe circuits with E, I, omega. This I, E, I, omega T thing that we just tried is very real in physics. It is a physics thing. It's not a huge part of this course. Like we're going to move on. But absolutely when I did, I mean, I is, it's called an imaginary number, but it's no more it's no more imaginary than pi or something like that. It's real. Okay, wait, sorry, catch me at 1 o'clock. I'm making a choice here. Hold on a second. Yeah, I think we can go back to, we're going to go back to the sheet now and just move on, at least for the moment. So the next, so we just answered J and K. Like, so our answer to K on the homework is yes, it is a solution. Okay, so once you put so that does suggest, if bottom line, if you're, it means anytime you write cosine, you could instead write e to the I thing. Like they are equivalent. This is called Euler's equivalence. It's true. But all right, so that's K. That's K. Sorry. Oh, wow. So we've done all that now. Okay. I'm going to pause on the vector stuff for the moment. You know what I'm going to do now? A slightly unusual choice. We're going to get back to the vector stuff soon. We need the vector stuff. All the practice with the cosine functions is kind of practicing like phase stuff that we talked about. It's a good practice, but I'm not inclined to go over it right at this moment. What I think would be more useful, whether you have done it or not, whether you've done it or not. Wait, is this true? Am I right? Well, no. All right, I'll just bang through. I'm sorry, I take it back. I'm going to bang through up until the vector stuff. I'm going to bang through the rest of this now. I don't know if I have anything interesting to say about it. You. Please, when I say bang through, I don't mean to rush. You can ask me questions, but I consider this sort of practice. I'm not sure there's a lot of interesting things to say about this, so bear with me. But definitely ask questions. And again, whether you've done this or not, this is for you to check your answers. If you did it, it's to help you if you didn't do it. Definitely ask me questions, but I'm just going to try to. I see we had 25 minutes. But it's really meant as practice with that phi term. And people are welcome. You know what? I'm going to just start scrolling out the answers. I'm just going to start writing them and I'll talk when there's something interesting to say. But you guys are welcome if you want points or whatever, just to. Oh, cool. Okay. Oh, cool. You guys are welcome. If you want to just start putting answers in the chat to any of them, like if you want to, you could put an answer to number 3, number 5, whatever, and I'll copy your, if it keeps you going. But I'm just going to like write out the answers as I see them and you stop me. Okay. So it won't be interesting. Okay. I'll pause for a second. I think for 2, make sure that you agree with my answers for 2 so I'm saying the 2 possible answers are t equals 1/2 second and 3/2. Make sure you're okay with that. Okay, but then I'll turn the page. Stop me if you want me to turn if you don't want me to. Blah, blah, blah. Now, I'm almost surprised. Do people, I actually would like to pause at least and say, does anybody agree? Can I just get any agreement or confirmation with answers 2 and 3? Because they seem just weird enough. I mean, I definitely don't have to say anything about it if nobody wants to do, but can I just get anybody to agree or disagree with answers 2 and 3 from math methods? I'll pause before I get any. Oh, so wait, so this is, I'm glad I asked. Wait, so I'm literally, wait for 3. So I am literally asking, and someone is very much saying that I'm wrong. And it may be, I had a feeling I might have made a mistake. So one person is saying that they think, so I definitely want feedback on this. I had a feeling I might have. So let me look again. I mean, and yeah, the answers do go on forever. What they are, whatever the answers are, they do go on forever. That's certainly true. What Yabo is saying, but I think the actual question's only asking for the first 2. Like, but now, did I make a mistake? Let's see, the cosine of uh, so wait, I may have made a mistake. Yes, no, I probably. Oh, wait, where the cosine is supposed to be 1. Oh, you guys are right. No, you're totally right, and I am wrong. No, I'm glad I asked. Okay, in other words, this, yes, that should be a 2 pi, and therefore this should be a 2. Yes, I do agree with Yabo and Kimberly. So I am glad. Oh, and Justin. Sorry. Oh, I'm sorry. And anybody who might be in the. Okay, right. So are we? So yes, thank you. There was a mistake on my part. Yeah, and the ultimate answers, and let me, like, the answers would be 0 and 2. That right? These ultimate answers are in seconds. The pies will cancel out. But are we? So we're good. So that was my mistake. I'm glad. All right. I was just doing that to see if people are paying attention. All right, I'm gonna go on more then, but stay with 20. Or I'll do something else if people tell me to. But that was 3. So now 4 is. Does everybody agree with that? Look, that's 3 or people, and we're just. Okay, that was. Oh, so I remember why we're doing this now. Right, it's not fascinating, but there's a reason we're doing this. I remember now. So I'll keep going if there's nothing else in the. Oh, there is. I'm sorry. Oh, cool. Okay, great. Thank you. Awesome. Okay. And again, all of you that put anything in here, whether you put it into private chat or not, please submit it. And also, when you do submit these things for points, and I should say to all of you too, the point thing really is working because those of you even who just say hello, but just like put that in every day, are racking up a lot of points. And there's just enough people that are just like not doing that it actually starts to make a difference. Just so you know. But when you do put something in, like, but it's also really it's just helpful on so many levels that you guys are doing that. But when you do, if you say, I put in the private chat, like the answer to a question, just tell me what the question was. It will also reinforce the whole knowledge in your mind. Like if you put in, I put in 0 and 2 for the faith, just write that. I put in 0 and 2 for the, anyway. All right. So that's that one. Here's why we're doing this, as sort of exercisey as it is. That's number 4. If then we go to number, yeah, it's number 4. If we go to number 5, 5 and 6, right? Okay. So if x equals 2, what is t equal? Okay, same thing. So like we're obviously just looking for patterns here to try something up, but this is all meant to be contrasted with the answers that we get in B. That's the point of this whole thing. But okay, so we get or if you, sorry, maybe, I guess that would be, so. Okay, I think that's my answer for that one. And stop me if it's wrong. I'm just going to keep going on. And then 6, the maximum value of x is 4, right? Now, I'm just going to see that again, that's like not, those are like plug and chugs or exercises or whatever, but the real purpose that we just did all of those is that then you're supposed to contrast with what happens in 6. Okay, and I will or will not maybe write out all the answers right now, but I just lost. Okay. But the whole point is, I'm sorry, that's all to contrast with what's in B. Okay. The main thing I want. Yeah. And let me pause for 1 second. So the main, whether we go over these individual answers right now or not, the main, I think you can see the main distinction between A and B is that in B, we introduce a phase shift of pi over 2 radians, right? Of A, in other words, of a quarter cycle, right? In part B, we introduce a phase shift of a quarter cycle. Now, we also introduce the 2 pi term, you know, next to the T. So that does up the ante even more a little bit. But the effect of the combined of the two alterations we made, the ultimate effect is all entirely on phase here, on where we're starting to measure our cycles, right? So every answer that's different that we get shows the value of phase. So again, we might go over the answers, we might not have time right now. But the one thing I want to emphasize is that in this class, that phase constant, that extra term, I mean, we went and, this came up earlier with the 3.5 or whatever. We call this extra term phi, lowercase phi or phi, like I have written right here at the bottom of the page. And it's going to come up a lot in the future of this class. On the web, sometimes it's denoted with something that looks like a lowercase delta, or is it really, it's actually something that looks like a lowercase delta. That's what it's used on the web. I just want to say that those of you who did homework 3, if you got help from the web, that's totally cool. That's totally encouraged. That's totally great. And especially if the web helped you, then it helped. And that's terrific. Hopefully at some point, you'll see the connection between what you did in homework 3 and what we're trying to do in class. That is to say, in class, we never introduced a delta. So a lot of the homework 3s came in with like a solution with work that had like this delta flying around in it, which is correct. Delta is another symbol that sometimes people use for what we use as the phi. But the phi in homework 3, I mean, again, I'm not, some of you, this doesn't mean anything to you, like if you haven't looked at homework 3 yet. And some of you are maybe annoyed that I'm saying this, but in homework 3, if your solution to the very first question had like a delta in it, what that does tell me you did good web research, and that's cool. And it also tells me maybe I didn't teach this as well as I could have, that you would need to do that, or blah, blah, blah. But some point, look back at your notes and see if what you did there doesn't also make sense with your notes. Because on the web, whatever you got on the web that has a delta in it, you then eventually, all of you had to take pains to show that the delta equaled 0, and then you crossed it out, which would happen in this class too. If you used a phi, we would say that for homework number 3, again, if you've done it, then phi, in effect, the phase constant there is 0. You don't have to worry about it all. The main thing of homework 3 is that since the differential equation, since the constant, I know I'm saying this fast and I'm saying the abstract, but in homework number 3, you're given a differential equation where the constant of proportionality is 121. The main insight of all of this is if the constant of proportionality in the differential equation is 121, then the angular frequency of the harmonic oscillator is the square root of 121.11. Like, again, that makes no sense to anybody that it doesn't make any sense to, right? But if it does make sense to you, that's the whole thing to the homework. It's just like, once you see second derivative equals negative 121 times like d or whatever, then boom, you're saying that's an oscillator. Its angular frequency is the square root of that 121 right there. And you don't need any phis or deltas to realize that. It's kind of what, this is a little bit of a digression. But I'm saying what now in class, we care about phi. We call it phi. On the web, they call it delta. Just if you want to like be navigating the class material, no, that's the same thing. Like whichever one you want to use, but no, it's the same thing. Now I'm going to say the role of this phi, this phase constant, where you start measuring is kind of like affects the answers just in exactly the way these two examples are meant to give. I guess since there's only, all right, since I have 8 minutes, I'll just quickly give the answers here. Hope they'll either be clear or they won't. But okay, so I'm just going to go on. But yeah, that was an excuse to give my little homework speech there. Just be careful what you get on the web. Like use the web to clarify class. Use the web even as a substitute for class if it's clear, but you got to know what it is that you need to know for class. You know what I'm saying. Y'all know what I'm saying. All right, all right. B given. right? I guess one thing I want to say is that 2 pi that we stuck before the t is kind of obnoxious that we did that. It's kind of, I mean, it's saying it, well, it's not obnoxious. That's its angular frequency, right? That 2 pi, that means 2 pi radians per second, right? This is how I look at these things. The 2 pi right before the t means that the angular frequency is 2 pi radians per second. That means this thing is cycling 2 pi radians every second. That means 1 cycle per second, right? That's what that 2 pi, whereas in the top, that's its rate is 1 cycle per second. Whereas in A, the rate was a half a cycle per second because it's just pi times t. I mean, is everybody, so they have two different rates. And that's why it's kind of obnoxious that like another fact's being thrown in. But this second oscillator in B is oscillating twice as fast as the first one, but also it got a head start. Like we didn't start measuring at its amplitude position. We started measuring it right when it was at equilibrium. I know that because that's a quarter of a cycle in. Those two facts together make for different answers, these answers, and then we'll be done for today. But yeah, it's kind of trying to show you how the phase shift like makes its difference right there. All right, so x equals. Right. So this one, right? You can see that like right when we started timing. In other words, right when we started measuring, it's already at the equilibrium position. Why? Because that's when we started timing. When it was at the equilibrium position, you could tell by that phase constant of pi over 2. I don't know if that. Oh, I should have done this in a different color, but anyway, that's the answer to that one. I don't know if this is clarifying anything. Oh, and that's yeah, and then. Now if x is, now we do the reverse. And it's only asking for a value of t, right? It's asking for a value, so I only have to give it one value. There are an infinite number of possible ones, but it's only asking for one. So blah, blah, blah. Oops, sorry. This is unfortunate. I have to go to the next page. It's such a bummer. So I'm just going to recopy. If you want me to go back, I will. I'm just taking the easiest, obviously, well, you get it. That's interesting, but possible. Maybe not, and that would be if I want the smallest positive image, and then I can. Well, I actually would be curious. Well, I'll stop right there. That's not an impossible answer. It may not be the most, may not be the answer. I mean, I should probably, well, I'll get a positive answer too, but I'd be curious if I made an error, if you guys got the same thing right there. I'll do one other thing. And we are going to stop. Was one, was it actually correct? Yes, it was. Yeah, this is, yeah, okay, this makes sense to me. So these are both, so I don't, actually, this is a good place to end. I don't know if you agree or not. Maybe we could pick up on this. Oh, chat, let me look in the chat, sorry. Oh, yeah, oh, did I make a mistake? Wait a second. Oh, maybe I got a mistake. Okay, I'm good. It might be easier if you draw a picture. Different people, it's very good if you draw a picture of cos and you can see it. No, that's certainly, and if it is easier for you, then that's great. Apparently it wasn't the fastest thing I could do, but that's great. Now wait, maybe I did make a mistake here. I know we have like 1 minute, but where did I make a mistake? I mean, my two answers are certainly consistent with each other. Let's see. Okay, did I write down the equation right? The equation is all right, very quickly. I know it's 1:30. I'll just see. The equation is 4 cosine 2 pi, yes. Okay, and we want a value of t for which x equals 0. A value of t for which x equals 0. Did I do the wrong? Oh, I'm doing for which x equals, I plugged in 4. That's my problem. Sorry. We want a value of t for which x, oh no, that was the one I was supposed to do. Sorry. So I did that right? Oh, no, yeah, so I'm doing number 8, value of t for which x equals 4. I plug in 4 on the left side. So I get 1. The arc cosine of 1 is 0 or 2 pi t. I feel like my answers are right. Let me see the chat. I don't see an error when I'm doing. You guys are saying a different answer. Let me see. Oh, you do? Oh, okay, so wait. So, okay, so I'm going to just say, for me, I got 4 as an answer for 6. Is this 6? I believe, what I want to say right now is I know we're about to run out of time, so we'll have to check again when we come 6. You got an answer 4 for 6. All right, wait. I want to address what Marissa said, but I'm actually confused which one she's talking about, so I'm going to leave that for the moment. Is it OG4? But I do want to say that for the most recent one that I just did, that looks funny, I actually think it's right. If one person does see, well, I mean, okay, so Yabo seems to be agreeing with what I'm saying. We will pick up here next time, but you should like, I don't want to confuse anybody. I feel like this is right, but it could be wrong, and you will start by finding the error next time if there's an error, but you want to follow the all right. Oh, fair enough. Oh, yeah. No, and I'm not insisting that anybody gets a negative. Like, you might want to throw away your negative time. In a way, that's what I got my negative time, and then I was like, oh, I better look to a next one. So I'm not insisting that anybody get negative 1/4. But if you do get 3/4 as your lowest possible positive answer, first of all, I think I agree with that. And second of all, it kind of actually makes sense that the one before is negative 1/4. But wait, so yeah, if you're getting 3/4, then I think we're on the same page. I think it's right, but I will go back and we'll pick up from here on Wednesday. I hope I didn't leave anybody with too much confusion or sorry, whatever that. But okay, it's time for okay. Thank you. All right, fair enough. Yeah, and my numbering is like totally confusing and annoying too. So, and we'll be done with this sheet very shortly. So I think we are really making tracks. You guys are being very patient. Rock and roll. I really appreciate it. I will wait to say goodbye. Like if you could say goodbye when you say goodbye, that would be great. I'll answer any quick questions and then we'll see you Wednesday. And we will talk about exam on Wednesday. Okay, but goodbye. Oh, thank you. Thank you. Bye.
Have a good day.
Thank you. You too. Bye. Bye, Kimberly. Bye, Jenna. Bye, Rachel. Bye,
Professor.
Shooty.
Have a
Thank
nice
you.
day.
Bye. Bye. You too. Bye. Thank you.
Bye, Professor.
Bye.
Thank you.
Bye. Thank you. Awesome. Bye. Bye.
Professor,
Yes, I'm right here. Yes.
you post something the past final exam in JJP 204. Is that like a book we have to buy?
You do not have to. Okay, thank you for asking. You definitely do not have to buy it, and I don't even think you need it. And it's for final. It won't even help for midterm. It would help. You don't have to buy it at all. But if it's anybody is, when we get to the final, if anybody is nervous or wants it, it has 3 old exams and all the solutions in them. It just helps. It's just a recommendation because it's just easier than me Xerox a million copies and giving. So it's like, so you don't have to buy it all. You probably won't need it. Most people won't need it, but it's just an option if it.
Okay, thank you.
Thank you. Okay, cool. Thanks. Okay, bye. Great job.